recording. Well, yesterday's problem was okay. This was the yesterday's problem. Sorry. Okay, yesterday we have already discussed. We have two rails and one bar sliding on these rails, and all these are situated in a uniform magnetic field with flux density B, which is given. And yesterday we found the electric motive force when this rail moves with some velocity v, and we found that it was 1.5 volts. And now we need to find force Fa, which is needed to maintain constant velocity of v of this rail. Well, main idea here is when this rail moves, for example, this direction, there occurs electric motive force, and due to this electric motive force, in this configuration, there occurs some current I due to the electric motive force, and this current I this current I also flows through the bar, and we know from the previous lessons that if we have some loop or some piece of conductor flowing through which some current in a magnet, and this conductor is placed in a magnetic field, we know this conductor will act some magnetic force Fm. And okay, in order to maintain the constant velocity, the velocity should be maintained constant. It means if velocity is constant, there is no acceleration of rail and of bar, and if there is no acceleration, forces Fm should be equal to Fa, and Fm from Ampere's law of force. From Ampere's law of force, Fm equals to I multiplied to the integral from 0 up to d. D is the length of our bar. Integral from 0 up to d of we denoted it as dr cross magnetic field B. Okay, these both are vectors. And let's back to our previous slide. The length of this bar is equal to d, and the length vector of this bar is directed, the current flowing this direction, and length vector of this bar is given as dr we can write as minus y roof dl. It means the length vector of this bar is directed opposite from the y. Here the direction of y. It directed oppositely from the y, and is equal to dr is equal minus y dl, and b, magnetic flux density b, let's move to previous slide. Magnetic flux density b is directed in z direction, and we write here well, in z direction, z roof b. Okay, we go back to our integral and we write I from 0 up to d, from 0 up to d, minus y dl cross z b, and is equal to current I, y cross z. Okay, let me write here y cross z gives us unit vector x, yes, and minus y cross z gives us minus x, unit vector minus x. I multiplied minus x multiplied, okay, integral from 0 up to d of dl gives us the length of the bar, which is d, and b is constant, multiplied by b. Or if we reorganize it, it will be minus x, which is a unit vector I d b. Okay, here we know the value of b, d value of b, but we know the value of I. Value of I is simply value of I simply computed through the Ohm's law. I is equal to electric motive force which occurred in our circuit divided by the resistance which present in our circuit. Okay, let me show you here. The load of 10 ohm is connected to our circuit, and if we go back here, electric motive force was 1.5 volt, 1.5 volt over the load of 10 ohm, which is 0.15 volt, and we can easily find magnetic force which is acting to our bar Fm equals to, we said, minus x, let me write in the form of vectors, minus x I d b. Okay, minus x multiplied I. Sorry, I is, of course, I is in ampere, not volt. amperes. Okay, multiplied 0.15 amperes. The length D was given as, okay, let me see the problem. D was 1.5 meters. Yeah, 1.5 meters here. Thank you. Okay. Multiplied D 1.5 meters and multiplied B 0.1 Tesla and is equal to 0.0225 Newton. And we know FA, magnitude of FA equal to the magnitude of FM, and the force which is required to put on the bar in order to maintain constant velocity is 0.0225 newtons. Okay, okay. And we have the third part. Okay, third part is easy. Mechanical power P. We need to find the mechanical power P required for generation. Okay, the third part. The mechanical power P is simply given as F multiplied by V. F is 0.0225 newtons and V was given as 10 meters per second, and this is equal to 0.225 watts. Or you can find power from the Ohm's law also, I square multiplied by R. This will give you also the answer 0.225 watts. Okay. What is what is our problem? It was here. Okay, let me open the book. And so okay. Well, yes, this was our problem. Okay, copy. And we go here. Okay, now we have seen this problem, and let us concentrate on one of them, on the first of them. First, the first configuration, A, can be also called as a linear generator. Linear generator. When we move bar with some constant speed v in some direction, there occurs. Okay, please mute your microphones. Okay, thank you. Okay, this configuration A can be thought as a linear generator, and when we move sliding bar in some direction, in our case in the direction of x, there occurred constant no, not constant, DC current I, and it can be thought as DC generator. Direct current generator. And if we look to the second configuration, to this configuration, to the configuration B, well, the main difference between these two configurations is in the first we have some load which is connected to our circuit, and we are putting some force and moving our bar. It means we are generating some current. In the second configuration, in the configuration B, instead of load, we connect some voltage source. We connect some voltage source V, and as we connected the voltage source, some current start to flow in this, for example, in this direction, and because of Ampere's law, this bar will receive, no, not receive, some force F acts to this bar, and this force makes this bar to move to in this case to the left. This is the principle. In the second case, this is the principle of DC motor, linear DC motor, or electric motor. Okay, let me open the new page, paste. So we will see now the second configuration, B. Configuration B. It can be thought as a linear DC motor, electric motor. And if we look to the next problem, the problem is more or less the same. First, we are asked to calculate. Okay, let me copy the problem itself also. Okay, here is our problem. Okay, I will put here a bit. We can reduce it a little bit and perfect. So let's read the text of problem. A linear DC motor is obtained by replacing the resistance R in figure 10a, okay, in this figure, resistance R by replacing with a source V with polarity such that the current flows in the same direction as the current in the generator. Okay, and so okay, the problem is the same. Two rails are separated at a distance of d 1.5 meters, and the battery with potential V 12 volt is connected at one end of the rails. Assume the rails are perfectly conducting, but the bar has a resistance of R 1 ohm. Okay, in this case, our bar has a resistance of 1 ohm. Okay, this bar has a resistance of 1 ohm. And bar is free to move. Okay, the magnetic flux density is constant and directed upward and equal to 0.1 Tesla. Okay, we need to calculate the force acting on the moving bar if the bar is held stationary, and if the bar is allowed to move, find the maximum velocity of the bar. Okay, and the part C, we can omit part C because part C is referred to more analytical mechanics. Let's look to part A and B. Well, if the bar held stationary, it means we are holding the bar and we are not okay. The bar is held stationary. We are holding bar and bar is not moving. The DC current flowing through the circuit equals I. If the bar is not moving, I is equal to V by R and is equal to, I think, 12 volt by 1 ohm is 12 ampere. And and the force is equal to current density J cross magnetic field B. Or okay, we don't use this. We use let's use the previous equation where force is found as integral of, okay, let's use this equation. Okay, force, magnetic force, as we did in previous problem from 0 up to D. dr cross b. Okay, I multiplied the integral from 0 again up to d. We said dr is directed to minus in the direction of minus y dl cross, and b is directed in the direction of z b, and this is equal to minus x I b and d, or is equal to minus x 1.8 newtons. Okay, the force acting to our bar is 1.8 newtons. Okay, we move to the second part of the problem. If the bar is allowed to move, find the maximum velocity of the bar. Well, part B. If the bar allowed to move, it will move in the negative x direction, because we found that force is directed opposite to the x direction, and consequently the bar will start to move oppositely to x direction. Well, and when bar start to move to the, in our case, to the left, because of the movement of the bar, there occurs in the bar occurs some electric motive force, which is equal, we know from previous problems, B multiplied V multiplied D volt. And this electric motive force, which occurred in our bar, should be balanced with the well, let's look, with the voltage source of B. Okay, let me, and with the, from Ohm's law, with the voltage drop on the bar, which is voltage drop on the bar is I multiplied by R. Okay, this electric motive force should be balanced with two voltage drops, which are V minus electric motive force minus I R should be 0. And from here we can find the current which flows in our bar when we allow it to move, and current will be equal to, so IR goes to the right hand side, V minus electric motive force over R. And if we replace here instead of I, if we put this expression, what we have Fm equals to, now I'm writing only magnitudes without vectors, I, B, D. And okay, instead of I, we put V minus electric motive force over R multiplied B, D, which is equal, instead of electric motive force, we put V minus velocity B, D over R, P, D. Okay, here, instead of electric motive force, we put this expression. And okay, F, we found F, F M is V BD over R. Okay, this is the force which is maximum, at the beginning of the motion of our bar. At the beginning of motion of our bar, velocity is okay 0. Okay, we are out of time. Let's resume. Okay. Well, we said this force is maximum when V is 0 or at the beginning of motion. As the bar starts to move, electric motive force equal to V V multiplied B multiplied by D is induced in the circuit, which reduces the current flow in the bar. Well, in other words, we can say that we start with a maximum force given here with the maximum force of this, and we at the end force should decrease up to 0 when the velocity is sorry, okay, let me right here, when velocity is maximum, when velocity is maximum, force acting on our bar should become 0, and when the force is 0, our bar will continue to move at constant velocity according to the Newton's first law. Okay, and in order to find maximum velocity, we take F equal to 0 and find the velocity. Here, if we take F equal to 0, what we have? What we have, if F is equal to 0, if this is 0, we have so V, voltage source V minus V B D over R multiplied B D will be 0. Okay, And this simplifies, this also simplifies, and we have v minus velocity bd equal to 0, and velocity will be equal to voltage over b multiplied by d, which will be 80 meters per second. Okay.
Teacher,
Yes.
resistor is equal multiply D multiply D. Why?
No, this is not resistance.
R is equal mu?
Well.
R bilen B'de kıskarıp gitti.
Okay. Look. Look. You are speaking about this part, yes?
Yeah.
Well, when we took force equal to 0, we saw that V minus VBD over R multiplied BD equal to 0. Yep.
Yeah.
Okay.
Bo'ldi.
We move this to the right. Also, we move R to the right, and they simplify each other. Okay, they simplify with 0, not each other. They simplify with 0. Okay, this was the principle of the linear electric motor, linear motor. Well, linear DC motor. Now you have a rest for 5 minutes, and we continue with new concepts, which are induced electric motive force because of transformer action, and also the AC generators, AC motors and AC generators. Okay, save. I will stop recording.